All right, so now that we have got a very quick understanding of what tree is, we have got an understanding of what binary trees are, what complete binary trees are. Let's now try to impose a tree structure on a list. So the idea here is that, look, the list of numbers that we have is definitely arranged in a list as always, so which means they are like sequentially arranged one by one. However, we are trying to view them with a certain lens so that it looks to us that they are in a certain hierarchy. Remember, trees have a natural organization which creates a sense of hierarchy. So we are saying that, okay, look, uh, though these numbers are stored in a list, exactly like earlier, however, let's view them a little bit differently. Let's think of them as though there's a certain hierarchy, and this hierarchy is captured as a binary tree. This may look very non-intuitive to start with. This may be like, you may be wondering, why are we doing this? But remember, go back to the motivation that we said, that for certain problems, especially problems where things are changing, the items on this list are changing, and we want to keep track of the, like say, the highest priority. It just turns out that imposing this structure, viewing the data from this lens of this tree structure, in fact helps us to solve these problems very efficiently, because we start seeing this, we lead to this viewpoint will lead us to a structure called heap, which will solve this problem very efficiently, right? So even though it may look little, let's say, curious at this point of time, but let's just do it. Very straightforward, the rules we are going to say. Basically, list, remember, is a sequential, let's say, storage of numbers. So start from 0, go until say in this case 15 values. I could have any numbers here, let's stick to numbers for now. So, I could have any numbers here. To me, these are just like a collection, because remember, many boxes connected to each other. Basically, that's list. We know this very well. Here, I've got the value as well as the index. Now, 15 values become, from a binary tree perspective, become a perfect binary tree, 4 levels, because 2 to the power of 4 minus 1 is 15. Now, what I'm saying is, let's fill this tree with the values on this list with this rule that I'm going to state now. Start from the top and go from left to right. So essentially what's going to happen is, I'm going to put my 12 at, let's say, the top node, the root node. 24 and 11 become the two children of 12. 13 and 18 become the two children of, let's say, 24. 9 and 2 become two children of 11, because again, because the structure. Then I have 15, 16, 1, 3, 5, 7, 8, and 9. So, basically just fill up from the left to right, top to bottom. Like I said, when I say fill it up, all we are saying is that, okay, look, this data is stored in the way it is. However, let's view it differently. Let's view that, there's this kind of like, we put like a transformation here. We're saying that, okay, let's view this in a way that 12 is the, say, the parent of these two. This is the parent of 13 and 18. This is a parent of 9 and 2, and so on and so forth. So imposing this hierarchy, imposing this structure is what we mean by imposing a tree structure. But very simple. You can do it, let's say, functionally. Just fill up the tree from left to right. Let's take a few more examples. Let's say I had only 3 items. Now 3 items would clearly make a perfect tree, because 2 to the power of 2 minus 1, 12, 24, 11. So all I'm saying is that, okay, look, let me fill the value 12 in the root node, value 24 on this left child, value 11 on the right child. Because again, remember, filling from top to bottom, left to right, right? So this is the tree that I'm looking at. I mean, this, when I'm imposing a tree structure to this list, a binary tree, complete binary tree to be precise, it is looking to me 12 has two children, 24 and 11, both of them are leaf nodes. Let's look at some more examples. That says 7 values in the list. Well, rule remains the same. So I start from the top, 12 goes here, 24 and 11 go to the next level, and then I have 13, 18, 9 and 2. Remember, just following the rule, start from the top, go to left, go from left to right. So 12, 24, 11, 13, 18, 9, 2. Like I said, again, we are viewing it as though there is this hierarchy, even though the storage is still in a list, and that's the important part. Now we already saw an example of 15 values, but let's look at it again. So 12, 24, 11, 13, 18, 9, 2. Make a correspondence here. Just look at it. Every value is following this rule. Now we have 15, 16, 1, 3, 5, 7, 8, 9. Exactly what we are seeing here, right? So basically, I'm just kind of proposing a rule here. Let's accept that rule and fill up the tree with the values in the list. But then clearly you will be questioning, and you're right to question that, look, this could have been done in many different ways. Why this specific rule? I mean, for example, I could have argued that, look, instead of viewing the item 0 as the root, I'm going to view item 2 as the root. And, maybe I'm going to look at item 1 and item 3 as its children, and so on. So another type of tree could have been created. Why this specific ordering? Well, this is where the heap property comes in. Basically, we are trying to create a complete tree, And this mapping that we are proposing here, go from top to bottom, left to right, helps us getting to heaps while maintaining the completeness property. So essentially, let's just, my suggestion would be at this point of time, let's just accept that this is the rule we are going to follow, because logically this will lead us to heaps. As we'll see later, by using this rule, we are creating a structure where there's a very clear relationship between the parent and the child nodes, and that becomes useful in programming later on. What happens if, let's say, I do not have a perfect tree forming? So far, whatever I looked at, say 3 items, 7 items, 15 items, clearly those are perfect trees. But what happens, let's say, if I have only 12 items in the list? Well, worry not. All I'm looking for is a complete tree, which means that, look, complete tree, I must fill from left to right. I will just take 12, 24, 11, 13, 18, 9, 2. When it comes to the last level, basically, I'll just start to fill from left to right, because that's where my nodes are: 15, 16, 1, 3, 5. So this is basically, as I mean, that's what I've done with the 12 item list. So there's item 0 is on the root, item 1 and 2 on level 1, item 3, 4, 5, 6 on level 2. Now this would have happened, for example, with just 7 values. Remaining 5 values go to item level 3, and the parent child relations are as shown. So basically 9, for example, has only one child, has only left child, this node here. This node here has no children. Let's take a few more examples. Let's say 8 items in the list. So clearly 8 will make us have 4 levels, because 1, 2, 3, that's 7. 3 levels have 7 nodes. The last guy goes on the 8th level. Remember, from the left to right property, complete tree, I will make this 15 to be a child of 13. I mean, this node 13. So, you see that this node has one child on the left side. That is on the, this level here, right? Similarly, let's say 6 items. Now you can create more examples of this sort, but just creating a few. 6 items, this 3-level tree. I must go left to right, top to bottom. So basically 12, 24, 11, 13, 18, 9. Yeah. So this node has only one child. This here is empty, right? Because remember, we are filling from left to right, right? So the point is, look, like I said before, this list is exactly as it is, but we are viewing it as though it's a tree, and a tree which has been filled up in this form. This is what is going to lead us to a heap. Like I said, the value of this will become more apparent as we start solving problems. But for now, let's just accept this as a rule, and I suggest we move forward. I hope you found this interesting. Do look at our website www.ybyte.in for more such content, and forever enjoy programming. Take care. Thank you so much. Bye bye.